Find the centroid of the area of the semicircle passing through the point 3 over root 2, comma, negative 3 over root 2, whose center is on the origin and diameter lies along the x-axis. So, as always, we want to draw a sketch of our graph here, and this says that the center is at the origin, that's right here, the origin, and the diameter this time lies along the x-axis, that would mean here, and the point 3 over root 2 comma negative 3 over root 2 is actually down in this quadrant right here because x is positive, y is negative, so it's this point right here. So notice our semicircle now is actually in these two regions of the coordinate grid, right? It's below the x-axis. So, first of all, we need to get what the radius of this circle is. So, using the equation of a circle, x squared plus y squared equals r squared, we can find the radius of our circle, given that we actually have a point on the circle, which we do. We're told what this point 3 over root 2 and negative 3 over root 2 as a point on the circle. So, substituting those values in and rearranging this for r, just a simple rearrangement equation solving to do there, we get r equals 3. So therefore the radius is at one of the points 3 comma 0 and the other one is at negative 3 comma 0, and there's one at 0 comma negative 3 on the y-axis there. Okay, so as before, we don't actually have to calculate one of the centroid coordinates, and this time it's actually the x-bar. X-bar is actually is equal to 0 because of symmetry, right? There's just as much stuff on the left side of the y-axis as there is on the right side of the y-axis. So because of that, everything balances out and x bar is actually going to end up at 0. The only thing is y bar will end up down here somewhere. So, just as a check, because y bar ends up down here somewhere, we would expect y bar to be negative, okay? So if you get a negative coordinate for y bar, then that's good because it should be, right? Because we're down in the quadrants or the region of the graph where y is negative. So we start with our y bar, then in this case we don't need an x bar, and we integrate, right, from this time we're going from lower negative 3 to upper 0, and we're taking these horizontal elements of width dy and finding out what the total area of this is, and therefore we're able to find the centroid from that. So this time we need left and right functions as before. So we need x2 and y1s here. So because of, I mentioned this in the other video on the other semicircle, we actually need to solve for x in terms of y given this equation of the circle. So if we do that, right, you can see, I'll just do it on the side here, right, if x squared is equal, or plus y squared is equal to r squared, this time though we're solving for x, so x is equal to plus or minus, as before, we need a plus or minus when we take a square root of r squared minus y squared. Now in our case, that turns out to be x is plus or minus, r is 3, therefore r squared is 9, take away y squared. So that is our function that we're looking at, plus or minus root of 9 minus y squared. And the right function, because x2 is in this quadrant, x is positive in this quadrant, this one gets the positive, and x1 is in this quadrant where x is negative, so x1 gets the negative root 9 minus y squared. So those are our right and left functions that we need to deal with here, are x2 and x1 respectively. So similarly to the last one, the bottom part is not easy to find the integral for. It's a very complex integral. It's not an easy one that follows one of your basic rules. So for that reason, we actually have to recognize this as the area of the semicircle again, and we can look at the fact that the area of a circle is pi r squared, therefore the semicircle is going to be half that, or half pi r squared. In our case, since r is 3, then half of pi r 3 squared is 9 pi over 2. and that's what we get for the bottom here. So we don't need to evaluate the integral here because we know what this is. Only because of symmetry that we can do these types of analysis here. We have to be careful here, but because of the symmetry of this, because we have a known formula for area of circles and semicircles, that's the only reason we can do that. Normally we couldn't do that with other centroid questions because we just don't have the formulas for areas of some of the other shapes. So the top one, when we plug this in as before, we're getting x2 is root 9 minus y squared. Take away a negative root 9 minus y squared. These two negatives make a positive, so you're adding them together, and you're getting 2 then, 2 of those, so 2 times y, root 9 minus y squared dy, all over, again, our area of 9 pi over 2. So notice this time the limits of integration are from -3 to 0, right? Bottom to top. Okay, but the only thing is, to solve this, we're going to have to use a little bit of u substitution here. So if we let u equal 9 minus y squared, then du dy, of course, is -2y, which implies that du is actually -2y dy here. But again, as before, if we replace everything in terms of u, we actually have to change those limits of integration. So 0, actually, the upper limit becomes whatever u is, 9 minus y squared, so that's 9 minus 0, because the y is 0 for our upper limit. So 9 minus 0 squared equals 9. And -3, that's 9 minus -3 squared, so that's 9 minus 9, which is 0. So we need to replace those. As soon as we replace u, we need to replace our limits of integration. Or as soon as we substitute in a u, we need to replace our limits of integration. So I put in u here now, so now my limits of integration go from 0 to 9, right? And because I needed a -2y, then I added a negative in front, right, to make sure that I get that -2y. Actually, I probably would have, what I would have done here is divided by a negative, but there would be one negative left over is what happens here. So we can think of it as just multiplying by the negative. That's all you need to know, is we need a negative in there because of -2y dy, okay? So then we can find the integral with our new limits of integration. So we find the integral, drop the integral signs once we found that. So integral, this is u to the half. So that's u to the half. So integral is u to the 3 over 2 over 3 over 2. But as I've done before in the last video on the semicircle, and the other ones actually, we can write that more easily as 2 over 3. It's better to do that. So it's negative. Notice the negative sign is still there. -2 over 3, u to the 3 over 2. Integrate from 0 to 9, all over 9 pi over 2. So we do this. The negative sign you can actually just take it in front. Just factor it in front, put a big bracket around everything, and then evaluate at your two limits here. So when I plug in or substitute in 9 to the 3 over 2, well, that's, as we've been doing, that's the square root of 9, which is 3, raised to the 3, which is 27, and 27 over 3 is 9 times 2, so we get 18 here. And notice the second term is all 0, as we've seen before, so we get just -18 over 9 times pi over 2. So if we, notice the negative sign, again, very important to remember here, the negative stuck around this time. I did not change the order of integration because my bottom number was actually smaller than my upper number, and that's what you want. So we do keep the negative here, so -18 divided by 9 pi over 2, if we do a little bit of math there, we'll see that this reduces to -4 over pi. Okay, and in keeping with, remember I said the last time that if we want to do x bar, we could do 4r over 3 pi. Well, y bar, same thing, right? We could do 4r over 3 pi, and our r in this case is actually 3, so here we get 4 over pi. Now the only thing is we actually need to manually stick in the negative here, because we know that it's below the x-axis, so it has to be negative, right? But this is a result that's, like I said, well known for circles, semicircles, quarter circles, that you can find x bar and xy this way, right? If you want to think of, for the quarter circle example, you can actually use this, and it's going to be 4r over 3 pi, right, comma 4r over 3 pi, right? But we want to be careful with that, with the quarter circle when you work that out. But the results are, that's the result that's known from using circles and symmetry arguments, I guess. So think about that when you do the quarter circle one. So I guess to wrap it up, then that is the centroid is at, we know x bar is 0, so somewhere along the y-axis, and it's at -4 over pi, wherever this is. And that would be, that's the centroid of the semicircle. All right.